All right, so this video is the second of the sort of circuit making videos, which mostly is just going to sort of put the sort of finishing touches, I think, on the stuff that we started in the last circuit video, which was mostly just getting our feet wet with the idea of of logic in the first place, and then truth tables, and eventually working our way up to thinking about logical sentences and logical circuits, and building some circuits with gates and all that good stuff. So, um, but this video will talk a little bit more about, all right, where where are these things actually used? Where and how are these circuits actually used, and how do you sort of make your own or engineer your own in order to do certain tasks, right? Beyond just, oh, I can put these gates together and make a circuit. That's nice, but to be able to say, all right, this really is the circuitry for real life tests or real life things we might want to do. So, um, so before anything else, let me just give you the quick reminder of our logical operators and the gates and all the whole bit. So, right. So the idea is that we've got four different kinds of operators or gates that we might use in order to connect propositions, right? So A and B in this case being called propositions, but basically that's just a fancy word for something that's either true or false. And remember, of course, we're using the notion of 0 as being false and 1 as being true. So you can do T's and F's or zeros and ones, whatever you want to do. We'll use more zeros and ones probably in this video. But and the operator and, just like of course it would in English, is a way of connecting two propositions, A in this column and maybe B in this column. If I want to say, well, what does A and B mean? Pretty much just mean what it means in English, right? When is this true? When is this statement, A and B, when is that true? Well, it's true only when A and B are both true. So you can see that in the bottom row here, that A and B is true only when, well, A and B are both true, right? And A and B is false in these three cases. And that's because one or more of them, or one or both of them, is false. So, all right, so try to sort of keep in mind, and is pretty easy, I think, to remember because it's one that probably most closely associates just with the English word. But try to sort of keep this in mind, right? That especially for two propositions, to be able to say, you know, these two, the combinations, in this case, the four combinations that you get from these two bits or these two propositions, in this ordering, get you zeros in these three places and one in this one place. So just sort of, as we review these, kind of keep these in mind. You want them to almost sort of flow naturally, that you sort of almost spot and say, oh, you know what? Well, if you want three zeros and a one, maybe an AND gate is your friend because, well, it does that. So anyway, okay. And in the sort of logic world, this shape, whatever you want to call that, is the usual notation for AND. All right, or, which is also pretty reasonable to just sort of say in English, A or B. So when is A or B true is how we might ask the question. Well, A or B, which is this notation here, is true, as you can see in these three cases, when A is true, or B is true, or both, right? So another way of saying it is A or B maybe is only false when they're both false. Right? So, and again, try to think about this again. Three trues and one false should maybe make us think, okay, maybe that's or. Or and, of course, are somewhat similar in that there are three of one type and one of the other, right? Except, of course, for and, you get three falses and one true. And for or, you get three trues and one false. So, when we're doing our activities today, if you sort of see something, you're like, I think I want three trues. Maybe an or would be possibly the way to represent that. But anyway, okay. And then the symbol for that is this sort of, I don't know, I mean, I don't even know what to describe that shape as, but that symbol uh, represents the OR gate. Okay, and then we had the NOT gate, or logical NOT as it sometimes is called. And this is the easiest one to understand, I think, because it just says do the opposite, right? Or it sort of flips from true to false or false to true. So if A is true, then not A, which is what the squiggle here is, not A would be true. Did I say that backwards? If A is false, not A is true. And if A is true, not A is false. So it's just, right. So anytime you sort of see something, you say, you know what, that's exactly what I want, but I want the opposite of it. Or I want, the inversion or the flip. Maybe not is the one you want to go for. Or if you're trying to say, is just maybe a single thing, you want to sort of say that it's false. Right? In other words, you want to say, I don't want A to be true. Well, then maybe not A, you're asking synonymously to say, when is A false? Same time that not A is true. Might be I know it sounds silly to say it that way, but for our constructions, this might be helpful. So anytime we have either going to insert the word not, or we kind of are looking at something and say, you know what, that's what I want, but I want the opposite of it. The not is going to maybe be inserted in there somewhere. Okay, and the triangle is used to represent not. All right, and then our last gate of the four anyway is this XOR, or exclusive OR, as it sometimes is called. And that is just to say, well, it's or, right? So it's still A or B. However, the X here indicating exclusively or. In other words, when is this true? When is X or B true? Well, it's true if A is true or B is true, but not when they're both true, right? So the exclusively has to be just one or the other. So if A and B are both true, no, then A XOR B is false. Right? And of course, in the event that A and B are both false, A XOR B is also false. All right. So, and again, looking at the result, I guess here, what will be most notable about the exclusive OR is that it is our way of getting two trues and two falses. So again, when we see this and we say, oh, you know what, I think I want this to be two trues and two falses, even if it's not exactly this order or arrangement, I might think about using exclusive OR to model whatever I'm trying to do. Okay, and the symbol for this is the same as the OR, except it's got this extra little, I don't know, crescent-shaped sort of character in front. All right, so this is where the last video left off, was playing around with this circuit applet and building some test circuits. And you hopefully had a chance to try these. Well, we did most of these together in the video, but that you tried some of them in the homework as well. The applet is just sort of a cute tool. Obviously, it's not something you need to use in order to do any of this stuff, but it at least gives you a little bit better sense, rather than just sort of writing them on paper, of, this is you're physically building something and turning stuff on and seeing lights come on and all that, just sort of as a nice visualization. So we'll use this a couple more times in this video as well. So now, I think we were mostly, for the most part anyway, using and constructing circuits that were sort of already pre-planned, so to speak. In other words, that, we just made this circuit and said, oh, okay, I want to do A and not B, and we built that, and that was nice. But where does this come from, or what does this model? Well, in this case, I just said it models X. Well, I don't know what the hell X is, right? So today, in this video, we're going to try to say more, what are the things I'm actually trying to do or check or whatever. In other words, rather than just saying this is X and Y and Z, I want to put meaningful things over here and say, what's the test, or what's the circuit I'm going to run in order to say, when is this true? Or when should I do Y? I should do Y when this is true, and I should not do Y when this is false. Okay, and we did do a little bit of that, right? We did sort of create or come up with the circuits, the logical sentences first, or logical statements for these characters, for doing some capitalization or a character like a $sign. So we're going to try to do a little bit more of that, and in a somewhat more advanced way. So what's sort of left is to say, well, what else? What's the rest of the sort of the circuit story is that not only do I want to be able to sort of understand how could I make these things like we've done with our simple examples of making characters, right? So we've already written the circuits, written the sentences, written the circuits for how do I maybe make capital letters or characters on the keyboard. And that's most useful when trying to determine the timing of when things should happen, right? So right now you're all watching this video on a computer of some sort, and if you were to, I'm not sure exactly what would happen in this mode, but certainly if you're in like a Microsoft Word or any sort of text mode, you know that if you hit, for example, the left shift or the right shift and the 7 key, probably a $sign is going to appear on the keyboard. So now we've already talked about sort of the circuitry of making that happen, and yes, indeed, there literally is a circuit under the keyboard. And so in terms of timing of when things are supposed to happen, binary circuitry, as we've been talking about, is of course used to determine when do I do stuff, and mostly that's based off of the user input, right? So why is your screen not advancing to the next slide right now? If you were watching this, if you were scrolling through these slides, well, because you're not hitting the right arrow or the clicking the mouse or doing something that would say go to the next slide, right? Right now, I'm not even touching the keyboard. But that doesn't mean that the keyboard isn't, or that the computer isn't still listening right now, so to speak, to say, is he hitting the right arrow? Is he hitting the right arrow? Is he hitting the right arrow? And it's waiting for me to, of course, hit the right arrow in order to know the timing of when to go to the next slide, right? Or to type a $sign. So timing, which I know doesn't sound like something we pause and necessarily think about, but it's obviously extremely important in terms of doing operations or making actions happen. I have to know, well, when the heck am I supposed to do this? Well, circuits are all over your computer that are more or less all just waiting and saying, should I do something now? Should I do something now? Should I do something now? And it's waiting for a true statement, right? So why am I not getting $signs all over my screen here? Well, because I'm not doing left shift or right shift and 7. Now that circuit is under my keyboard right now. In other words, right, there's wires coming out of the left shift key and the right shift key. They're being fed into an OR gate. This is really true. They really are. And the result of that is being fed into an AND gate that has a wire also going into it from the 7 key. And so it's waiting. It's saying, right now this is false, right? Right now, this logical statement right now is false because I'm not doing the correct things in order to flip this over to true, right? And even if I just hit the left shift key, which you can't tell, but I'm doing that right now, and then I'm going to hit the right shift key, well, I still don't get $signs because even though some of the circuit is now turned on, right? This portion of my logical statement, when I hit the left shift key, oops, I hit the caps lock key, the left shift key, right? This part of the logical sentence is true when I hit the left shift key. But it's also waiting for the 7 key to also be hit, right? Remember, and is only true if both pieces are true. So of course I'm not getting a $sign, but that doesn't mean that it isn't listening constantly for, gee, maybe my circuit will be connected, right? Maybe that circuit that's under the keyboard that says make a $sign, it's waiting to get electricity to flow through it, just like a light switch is waiting for you to switch it to allow electricity to flow and turn a light bulb on. It's waiting to hear, it's waiting to know, should I make a $sign? Should I make a $sign? And if I did hit the shift key and the 7 key at the same time, for a brief moment anyway, that circuit turns on. And that's how, of course, the computer knows, oh, now's the time I'm supposed to make a $sign. Okay, so most of the timing aspects, first of all, it's all binary because it's all these circuits. But also, a lot of that's due to user input, right? So user interactivity to say, when should I do stuff? Now, of course, I might give a command that requires many subtasks to happen, all of which would also be would be timed out with circuits, right? It would say, oh, okay, maybe if a task that I'm going to do involves 5 subtasks, then there's a timing mechanism in the computer to say, okay, start on the first task, and when you reach the end of the first task, go to the next task, and then go to the next one, and then when it's all done, you're done. So what are some of the other tasks, though, besides just initiating timing, that are probably part of many of the even basic or more complicated tasks that I might have to do that also use binary circuits? Well, some of the common things, and we're going to explore both of these, it would be to do, well, what if I just want to make some simple arithmetic, I guess I'd call it, comparisons to be able to maybe compare two numbers and say, are these things the same? Or maybe I want to know, is a number, bigger than a number like 5? So I want to know, your computer is going to want to know sometimes an answer to a question like this. Why would it want to know, are two numbers equal to each other? Well, maybe again, this is related to the timing of when am I supposed to do something, right? You can probably relate to the idea that if I want to set a timer or notification or a reminder on your phone, you say something like, remind me at midnight to, whatever, to take a shower. Of course, your phone is more or less constantly asking the question, is current time equal to midnight? Because it's wanting to know. Am I supposed to remind you to take a shower right now? I don't know. Well, for a while, for most of the time, the answer is nope, 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 nope. But when it actually becomes midnight and current time equals midnight, it says, oh, that should turn on, right? That should for the first time now be a true statement, and therefore I'm going to broadcast a message or a reminder saying, oh, it's time to take a shower, right? So this is a very reasonable thing that your computer, believe me, millions of times a day, is asking to know, are two numbers the same, or is one thing equal to another thing? Because it needs it in order to help it do some decisions of, when should I do stuff or how should I do stuff. Okay, but how do I know that, right? Again, we're trying to think very basically here and very low level with circuits. How do I write a circuit that tests, are two numbers equal to each other? I know it sounds like a very simple concept, and as a human being, we don't have to think twice. If I say the number A, B here is maybe the number 3, and I'm asking, is 3 the same as 2, right? The binary number 2. I'm like, well, no, it isn't, right? But we have brains, and we can think, and you know immediately that 3 is not the same as 2. But how the heck does your computer know that? Remember, your computer is, while very good at doing computations, is really, really not smart, right? It has no natural human knowledge about anything. It can only do stuff or know stuff that we tell it. Okay, so we're going to want to explore a little bit of that. Maybe it's not that I want to compare two numbers, but I want to compare one number to fixed quantity of some sort. So maybe I'm waiting until I have enough memory in order to do something. So I'm going to know, is it true that the amount of memory I have is more than 5? And maybe once that becomes true, I want to do something, save something to that memory or whatever it might be. So another common thing we want to maybe be able to do is say, is a number bigger than or less than or maybe equal to a fixed number, right? And I should say when I'm saying A, B, C and whatnot here, I'm just referring to binary numbers, right? So when I say, is ABC bigger than 5, what I mean is a binary number that is 3 bits, right? A, B, C, is that bigger than 5? Okay. All right, and then if I can do some comparisons, which is what I might call these guys, what's the only real other thing I need to be able to do is some basic arithmetic or some computation. So a good question, how do I add a 3-bit number to another 3-bit number, right? So ABC plus DEF, right? How do I actually do that? Again, in our world, we know how to do addition, but I have several issues. One, this is binary, so I'm going to have to figure out how do I add in binary. So even as a human being, I'm not totally sure maybe how to add in binary. So that's a problem. But another problem is, again, remember, computer doesn't know. Computer did not go to second grade and didn't learn actually did not actually learn how to add. So I have to also come up with some circuit that's going to say, all right, if you have a 3-bit number and you want to add it to another 3-bit number, give me your two 3-bit numbers and I'll illuminate the answer. I'll run it through my circuit, and the output of my circuit will be the sum of those two numbers. Which, again, pretty neat. I know that doesn't sound like high advanced stuff, but it's going to be somewhat remarkable that even we can come up with the circuit that's going to do this addition problem. And I promise you, it's the same circuit that's in your computer, that's in your phone, that's in a basic calculator, that you might have an app for on your phone, or just an actual calculator. So, all right, so we'll work up to that. That's a little trickier. All right, so let's start basic. So I'm going to ask you to do some of these problems, of course, in the homework, and surely on the exam in some format. So I have a bunch of examples here. I don't have there's not a lot of quote-unquote notes to be able to give you, but I'm going to do a bunch of examples, and I think you'll sort of get the strategy, or at least, generally what are we doing each time, so that you can do this yourself. So, all right, so let's start easy. Let's say I have a 3-bit number, ABC, right? So it could be, so this is the ones bit. So I know it's been a little while since we did binary, right? But remember, a binary number, we're not going to deal with really big numbers, right? But a binary number, right, each digit is a bit, so it's either 0 or 1. And remember, the first digit is the ones bit, or in other words, it's worth 1. The second digit is the 2s, so a 1 here is actually worth 2. And the third digit is the 4s, and so that the A bit in this case would be worth 4. Okay, and you could keep going and do more, obviously. So a question that maybe your computer wants to know sometimes would be, is the 3-bit number I'm looking at? So, right, so you imagine this is a quantity that's maybe stored in memory, that's, whatever, it's some data from somewhere, and you want to know if it's equal to 3. So ABC is, these are bits, so these are all 0s or 1s. So it's reasonable perhaps to want to know, hey, is this actually the number 3 in our world? The ABC, is that 3? Because maybe when it's 3, I'm supposed to go do something. All right. Well, how do I explore this? Again, sometimes you have to almost like untrain your brain to be like, well, we'll just look at it. You'll know if it's 3 or not. Well, we can't do that, right? We have to really dumb this down and say, all right, computer, A, B, and C are bits, right? They're either 0s or 1s. So I need to physically come up with a circuit that's going to basically light up when ABC is 3 and not light up when ABC is not 3. That's our goal, and I should have probably sequenced this a little bit better so the answer wasn't at the bottom, so maybe don't look towards the bottom of the slide. But ultimately, I'm going to come up with a circuit that's going to say true or be on when ABC is 3 and off otherwise. All right, so what's our strategy? Well, let's explore what this actually means just in for our own understanding. So to ask, is ABC 3? Well, what is 3 in binary? Well, 3 in binary is 0, 1, 1, if you remember. So in order to know, is ABC 3, the number 3 in our world, I'm really asking, does it match, right? Is A 0, is B 1, and is C 1, right? That's the only way that ABC, this binary number, is 3, would be if A would be 0. So I need A to be 0, or again, false if you want to think more about true and false. I would need A to be 0. I would need B and C to both be 1s. Okay, so I know that's not rocket science, but it's worth dissecting at least to say, all right, in order to know when should I say yes to this, or when should I say true, yes, ABC is 3. Well, there's only one possible combination of 0s and 1s for my 3-bit binary number. That's actually the number 3, and that is that the first bit needs to be 0, and the second bit and the 1s bit and the 2s bit both need to be 1s, right? So I'd need A to be 0, B to be 1, and C to be 1. Okay, so that's not too bad. So I'm really just going to try to link up what I said in these last two lines here into a circuit or into a statement. So what is it that I need for the circuit um, to check, is ABC equal to 3? I think the circuit I want to use is just to say, all right, well, A needs to be 0, which means I need not A to be true. I know this is where it sounds a little funny, right? But if I say I need, which I do, I need A to be 0, then what I'm really saying is I would like not A to be true. Okay? But I need more than just that, right? Not only do I need that to be 0, I also need B and C to both be 1s. Or in other words, or to both be true. So I think I would say, all right, I need not A to be true, and I also need B and C to be true. So and this is where, again, I'm sort of trying to think about, maybe don't look at the A for a minute, right? But when I say, all right, well, B and C, these could be 0s or 1s. They could be true or false. But I need them to both be true. In other words, I only want this result to turn on, so to speak, or to be true, if they're both true. Right? That's the only time I want to say, yes, the number is 3, is if these are both 1s. So again, this is where I'm asking you to think back to the logic tables, right? How do I say, oh, only when they're both on do I want the result to be on or true? Oh, how about I use the and? Because and is only true or turned on when each of the inputs is turned on or is true. All right? So so I think, hopefully this makes sense, right? That the circuit that I would then check for, is ABC equal to 3? I think should just be this circuit, which is to say, is not A and B and C. If that's true, right, that logical sentence, if that's true, I want you to light it up and say, yes, ABC is 3. Now, if it's not true, then it should be turned off. It should say false. ABC is not 3. All right? So maybe it's useful, actually, to do a quick little circuit plot of this thing just to have a nice little visual to go with this. So let me grab, we're going to probably do several circuits today, so let me grab 3 switches for A, B, C, which I'll just do in order, A, B, C, all right? And remember, that's the number that I'm trying to say, is it 3, right? So is A, B, C, maybe I should do them next to each other. That probably would actually maybe make more sense. Right, A, B, C. All right, so I know we usually do them on from left to right, but maybe since it's a 3-digit number, it makes more sense for me to put them next to each other. Okay, so what did we just code up? We said in order for this to be 3, in order for this to be the number 3, which, I mean, spoiler alert, we know that's the number 3, right? So that I have off, on, or 0, 1, 1. Okay, but what did we say? I think we said in our notes, right? We said, I think the coding that I want to do is not A, so in other words, take A and not it, and then join that with an and, the result of doing B and C. So let's see if we can translate this guy. I think we're pretty good at doing that at this point. So B and C. So this is A, B, C, right? So B and C. So let me grab an and here. All right. So all right, so that's B and C, which doesn't look fantastic, but it's okay. So that's B and C linked up. And then what else did I say? I wanted to do the not of A. Okay. And then I want to link these together with one more and, right? So I wanted to say, and it's the and of these two characters, right? So we go. Okay. All right, and let me grab a light here. All right, so I've linked up, I think, the right circuit here. And, right, so the idea, remember, this is our number A, B, C. And they're all off right now, which means they're all zeros. So this is the number 0, 0, 0, which of course is 0, right? So it's good, the light's off, right? It's not the number 3. But if I try to sort of play around and say, all right, well, let me check other numbers, right? So maybe instead of the number 0, 0, 0, maybe I have the number 4, which is that number, right? That's 1, 0, 0. And good, right? It says, no, 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 that's not the number 3. All right, so I play around and say, okay, how about I do the number 5, 1, 0, 1. It says, nope, nope, still not 3. That's the number 1, right? 0, 0, 1. It said, nope, 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 not 3. But I think if we test our answer, which is to say 0, 1, 1, if you notice, the light turned on, right? So for the first time of all of the little experiments we've done here and playing around with this, 0, 1, 1, that's one that makes the light go on. So quite literally, this is saying, yes, you have the number 3. And any other combination, right, that I do here is going to result in the light being off in all the other combinations. Perfect, right? So this is exactly the correct test, so to speak, for is this the number 3? All right? So anytime your computer wants to test a number and if it wants to know, is the number I'm working with the number 3, it's going to feed it into this circuit and, report either yes, yes it is, or no it isn't, or whatever. All right? Okay, so let's flip me back over to the notes here. All right, so that's maybe what I would do if I wanted to check if a number was equal to a fixed value like 3. All right, now how about what if I wanted to check maybe is a number bigger than some other number? So maybe instead of checking if it's equal to 3, I might want to do a quick check to say, is the number I'm looking at, is it bigger than 4? Again, maybe the idea is that once I reach a certain value, I want to do something. I want to say, oh, okay, now I'm ready to whatever. So again, just to get a strategy for how should we maybe proceed with these characters is to say, well, all right, how do I know if the number ABC is bigger than 4? Well, maybe I should imagine or write down what numbers are actually bigger than 4. In other words, what are the combinations of A, B, C that would say yes, for which I'd want to say yes, that the number is bigger than 4. So if you think about it, bigger than 4 means, of course, 5, 6, or 7, and I think I wrote out the binary of each of those numbers there, 5, 6, and 7. You can see there on the screen, right? So 5, 6, 7, and that's it, right? I can't be more than 7 because with 3 bits, 7 is the biggest number I can make. So I say, all right, fine. So I want to come up with a circuit or a description of these 3 numbers. In other words, I want to say, all right, I want this to be true if I'm in this case, any of these 3 situations. So this is a little trickier, sort of, I guess, in that I have to now describe not just one situation like we did in the last example, where I just had to describe, I only had one possibility. Now I have 3 possibilities. But okay, this is actually, well, as you can see below the answer, it's actually easier, but I have to think a little bit more perhaps at the onset. So what's true, or what do I want to say? All right, so it's true if I'm in one of these 3 situations. What do these have in common, or what do they have different, is sort of a good question to ask yourself. So when I look at these 3 numbers, these are my 3 yeses. These are my 3 times I want this circuit to turn on and say, yes, ABC is bigger than 4. One thing you might notice if you just sort of look bit by bit is that the A bit in each of these 3, the first bit or the 4's bit, has to be 1, right? Because it's always 1 in all 3 of my possible scenarios, right? So I need A to be true. In other words, I need A to be 1. That's a fact. All right, but what else do I also need to be true? Well, what could be said about B and C? Well, let's see. If C is 1 and B is 0, I want it to say yes. If B is 1 and C is 0, I want it to say yes. Or if they're both 1s, I want it to say yes. So I think, again, try to think about our logic gates. Let's see, this says either one of them, or both of them. And that sounds an awful lot, I hope, like the OR gate, right, or the OR connector. Because what's true when I think about just B and C, B, the last two bits here, I say, well, I want it to be true if one is 0, the other is 0. I'm sorry, one of them is 1, one of them is 1, or both of them is 1. I want it to say, yes, you're bigger than 4. All right? So I think all I want to say here is that how do I know if the number is bigger than 4? You need A to be 1. So in other words, you need A to be true. And then what else? We need B or C, or both, to be true. But that's exactly the description of the OR gate, isn't it? B or C or both is true. Okay? So I think actually the circuit for is ABC bigger than 4 is just right here. You need A to be true. So you want A, when should this be true? When A is true and when B or C is true. All right? So I think that should do it. That should. I won't build the circuit maybe for this one, but if you switch this guy over to a circuit in the applet and did some testing of the numbers, 5, 6, and 7, I think this circuit would say yes, it'll turn on when you do these three numbers, and it'll turn off when you're not one of those three numbers. So that's a perfect check to say, oh, okay, this will tell me, or this computer will know, oh, okay, that's how I know if it's bigger than 4. All right, so one more example, at least of the basic comparing, is how about less than? And this was a little trickier. So what do I have here? So if I want to check to see is a number less than 3. All right, again, I'll adopt the same strategy, which is to maybe make a list of the numbers that are eligible. In other words, the numbers for which you want this to be true. So let's see, less than 3, of course, means 0, 1, or 2. Right? So the numbers in question are these three. So I'll use a similar strategy that we used in the last problem, which is to say, let me look at the numbers and let me scan what do they have in common and what do they have different. So here I might say, well, all right, how do I know if ABC is less than 3? I'd say, all right, well, A in each case has to be 0. We can sort of immediately hopefully see that. So you must have an A of 0, or in other words, you must have A false. So A needs to be false. And then what else? Let's see. So for B and C, they could both be 0, or one of them could be a 0 and the other one a 1. So in other words, the only thing I don't want to have, if you look at it that way, is I don't want to have a 1, 1. So I don't want to have B and C both 1. Because that would actually make the number 3, wouldn't it? Right? 0, 1, 1 is 3. So one way of saying that, I think, is I could either try to say, well, what does this mean? Either 0, 0, 0, 1, or 1, 0. Okay, so you might go the route of an OR, I suppose. And it's sort of the opposite of an OR. You could try to get it that way. But I don't know. To me, it made most sense to say, well, what did we just say in English when we described this? I might say, well, you don't want them both to be 1s, right? So B and C could be anything, but except you don't want them to both be 1s. So that sounds an awful lot like saying, don't do A and B. In other words, what do you want it to be true about B and C? You want it to not be that they're both true, or that they're both 1s. All right? So if I link this up and say, so what is it that I need again? I need A to be false, and I also need not A and B to be true. So if I put those together, the circuit for checking am I less than 3 is as simple as, or this isn't quite as simple, but if I put it all together, I think, what am I requiring? I'm requiring A to be 0, so I'm requiring not A to be true. And I'm also going to require that not both A and B be true, or 1s. All right? So it's a little more of a mouthful. When every time you have to insert the knots in there, you get a little more complicated, I suppose. um, so let me build this guy. Um, all right, so I still have my thing here, my original input here, right? So I want to do so it's A, B, C. So I still want to do not A, so I'm going to leave that alone. And then I still want to do and, but I think I wanted to do not A and B. Right. So let me throw one more not in here. We'll see what happens. So let me grab one more not. And I'm going to try to fit it in here, hopefully. So let me take this connector off and say, all right, so I wanted to do A and B. I'm sorry, B and C, but I wanted the opposite of that, or I wanted the not of that. All right, so I put a not there, and now I'm going to feed this in with the rest of this. If it'll let me. Ooh. Oh, okay. Oh. Okay. All right, so let's see if I have this right. So I'm doing not A, and that's part of my overall and here. And then over here I'm doing A and B, but I'm flipping it. I'm saying, okay, but not that. Right. Okay. And I'm feeding these both into one last and, which is connected to my light. All right, so the idea was that this was supposed to check is a number less, right, is our number less than 3? So hopefully this will come on when I have the numbers 0, 1, or 2. Hopefully this will say, yes, yes, you've got it. And hopefully in all other situations it'll say, no, no, you don't have it. So right now this is the number 111, right? These are all turned on. So of course it's saying this is the number 7, 111, and good. It's saying, no, 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 that's not less than 3. So if I turn, let's say I turn that one off. Now this is the number 5, right? 1, 0, 1, and it says, nope, nope, that's not less than 3. And even if I turn this guy off, that's the number 4, right? 1, 0, 0, and it says, nope, that's not 3. All right, but if I turn them all off, I think I'm going to get the number 0. So hopefully my light turns on, and it does. So good, right? So it's detecting. It's saying, oh, yep, that number that you've coded in here, I guess, is indeed less than 3. It's the number 0, actually. And if I turn this on, this will be the number 2, right? 0, 1, 0. And it says, yep, yep, that's less than 3. I should probably check all of them. So this would be the number 1. It says, yes, that is less than 3. But as soon as I go up to 3, if I turn this on, I again flip back and I say, nope, you know what? That's not less than 3. And it isn't, because it's the number 3. All right, and you can obviously play around with this and do any other sorts of combinations of things, and double check, of course, that yes, this is the correct, exactly the correct circuit to determine, am I less than 3? Okay, so now I should say, I didn't, I guess, do an example of this, but if there's a bit that you don't care about, in other words, you just want to know, or you just want to say, well, that can be anything, then just omit it from your sentence. So I don't want you to always get in the habit of saying you always need to have A, B, and C, or however many bits you're looking at. They don't all always have to appear in your answer. It could be that if you don't really care what one of them is, in other words, it's okay if it's 0 or it's okay if it's 1 in all situations, then just omit it from the from your sentence down here at the end. All right. So for example, maybe I feel like I maybe should have done a quick one of those. So let me just actually morph this example into one that makes sense to do this. So I'm going to cheat here a little bit and just change this problem ever so slightly, which is to say, what if you wanted to check if a number is bigger than 3? Aha, okay, so I didn't change much here, right? What are the numbers bigger than 3? Well, it's all of these guys, right? But it's also the number 4 I should throw into the mix here, right? So 4 is 1, 0, 0, right? Okay, so now that's my list of the numbers that I'm talking about. The numbers that are bigger than 3 is 4, 4, 5, 6, 7, right? So when I approach a question like this, right, I say, all right, how do I know if a number is bigger than 3? Or in other words, how do I know the number's 4 or larger? I'd say, all right, fine, here's the numbers. And again, I'm going to do my same trick, which is to just scan and sort of say, all right, well, what do things have in common and all this other good stuff. So as I look here, right, hopefully one thing jumps out at you, which is that oh, this is still true, right? I still need A to be a 1, right? So I still need A to be true. Okay, so that's still valid to say that. But what would I say about B and C? Well, let's see. B and they could both be 0. I could have 1 0 and one of them be a 1, or they could both be 1s, right? So if you're trying to think here and say, okay, so what gate is that, or what do I want to do with B and C? Well, what do I need B and C to be? Well, I think I just said, right? They could be both false or both zeros. One could be false and one could be true, or they could both be true. In other words, I think I just covered all 4 scenarios, right? So I don't need any requirement on B or C, right? B, they can literally be anything. I have all 4 combinations of what B and C might be, and they're all in. As long as A is 1, I'm good. And actually, if you think about it mathematically, how do I know that I've achieved a number that's 4 or higher? Well, if the 4 bit is a 1, then you're already up to 4. So whatever happens after that, that's just adding even more. So the answer will always be yes, you're bigger than 4. So just so you can do easy problems and you don't get too tied up with, oh my gosh, where is everything? What do I need to be true about B and C? Nothing, right? I have no requirements for B and C. So we just need that A is true. Oh, maybe I shouldn't have erased that. Maybe I could say, and what else would we say? B and C can be anything. Okay, or sort of no restriction. Okay, so how am I going to build my circuit then? So how do I know when ABC is more than 3? Well, the only thing I need to make sure of is that A is true. In other words, I just need to make sure A is is yes, or is a 1. So what's the circuit that I'm going to check? As funny as it looks, just that, right? So how do I know when ABC is bigger than 3? Just check if A is true or if A is 1. If it is, the answer is yes. If it's not, if it's a 0, if it's false, then your number can't possibly be 4 or bigger, because if there's a 0 here, the most you could make would be 3. All right? So, I mean, it looks a little funny because it's just one thing. But that would be the answer to this question, and that would be the circuit you would check to say, is my number 4 or larger? Just check the 4-bit. And just say, if it is, then yes. If it's not, then no. All right, so where did I leave us off? Right. So that's the story, I think, for comparing values, comparing numbers to sort of specific values. Now, one other thing we might want to be able to do is not just compare numbers to fixed values, but also maybe just to other numbers, right? So let's say we have 2 binary numbers, A, B, and C, D. And maybe I want to check, well, are they the same as each other, right? So no longer do I want to check if they're compare them to a number. I want to compare them to each other. So how do I know if AB is equal to CD, right? So this number, how do I know this binary number is equal to this binary number? Well, I think I would just want to check digit by digit, right? The only way to have, even in our number system, the only way to have 2 numbers equal to each other is to say, well, they must agree in every sort of digit, right, or every place value. So I really want to say, how do I know if AB is the same as CD? Well, I really want to check, well, is A equal to C? And is B equal to D? Right? That's pretty much what I want to know. All right. Now, how do I check for equality, though? That's a sort of new, I think, right? We've been dealing mostly with, um, gates or, just doors and things like that, or comparing to numbers. But how do I compare if two things are equal to each other? Hmm. I may have to think about that for a minute, right? So, well, let's think about this, right? When do I want this to say yes? Yes, A and C are equal. Well, remember A and C are both bits. They're either 0 or 1. So I think, hopefully this is believable. I want to say yes or I want to say true to this statement if A and C are either both zeros or both ones, right? Those would be the only two situations where I'd want to say, yes, A and C are equal. I'd want to do that if they're both 0 or if they're both 1. So obviously I would want to say false or say no, they're not equal if they're not the same. In other words, one of them is a 0 and the other one's a 1. All right. So I think this is a summary of what I just said, right? So how do I know when A is equal to C? Well, if they're both 0, I want to say yes. If they're both ones, I want to say yes. But if they're 1, 0, and 1, 1, I want to say false. All right? Well, look at this table, and again, try to reference our standard logic gates and truth tables. This truth table should look kind of familiar in that it kind of looks like the table for A, X, or C. Remember, the exclusive OR says it's true when one of them is true and the other's false, but it's false if they're both true or both false. So I think I've got actually exactly the exclusive OR table. However, every one of my answers is flipped, or it's the reverse of what I wanted. Okay? So I think if I use A, X, or C, which now this is the A, X, or C table, then what I really want to do in order to make it look like the one I want, which is this one, is if you just notice, right, each one of these, TFFT, I want it to be FTTF. So if I just throw a not in, remember not says flip everything or reverse everything, I think we've just discovered that the way to check if A and C are equal to each other is by evaluating the circuit not A exclusive or C, right? So A exclusive or C is going to do exactly the opposite of what we want. So if I flip it and say, okay, switch all those, I get exactly the table I was looking for, which is my test for, are these two bits equal to each other? All right? Okay, so similarly, I can obviously make the same statement for B and D, right? So how do I know if B and D are the same? I'm going to check not B, X, or D. All right, so if I put everybody together now and say, how do I know if these two numbers are equal to each other? I'd say, all right, that means saying A has to be the same as C and B has to be the same as D. So I need those to both be true. So I put an and in between them. And then we just explored, right? How do I check if A is equal to C? That's the same thing as checking not A exclusive or C. And then similarly, how do I check this? I would check not B exclusive or D. So finally, to throw this whole mess together and say, so okay, how do I check if these two are the same numbers? I just want to do both of these things. So I'm going to put them together and say, all right, do this test and this test. All right? So maybe we should see this one in action. So, oops, oh no, I've lost that one. Oh, maybe I can get it back. I can't. Okay. So just relaunch this guy. So if I want to build this circuit, let me grab a bunch of switches, and maybe I'll do it vertically, just because it's sort of a pain to connect those things. So here's going to be my number. Let me space them out a little bit better here. Okay, so this will be my number AB, right? So A, B, and this will be my number C, D, right? So again, remember the idea is as simple as it sounds, I want to tell the computer to know how is it going to know, hey, the lights are the same up here as you see down here, right? I think the circuit that we just explored should do it, but let's check. So what did we agree on? I think was that I was going to make do exclusive ORs and say, all right, feed these guys, feed A, B, oh sorry, feed A and C into one exclusive OR, and feed B and D into the other one. Okay, and these are now going to check, right? These are now producing, right? If they're both, if one is true and one is false, or if one is 1 and one is 0, these are off. I'm sorry, these are on. And if they're the same, then these are off, which is what you see right now, because these are all off, right? This is 0, 0, and 0, 0. So, all right, but then what was I going to do? I was going to say, wait a minute, that wasn't it, though. I wanted to flip them or reverse them. So let me grab some knots here. Okay. And I was going to also knot this one. All right, and then to join them together, I was going to say, okay, and both things have to be true. So let me grab an and here. Okay, and let me grab a light. Okay, and it's always a little more dramatic to, to do one that's going to be false. Oh dear. What did I do? Zoom out. Okay. Okay. All right. Well, not sure why I can't. Okay. Click on this. No. Okay, so I've lost control of this of this thing. Okay, well, you saw me build the whole thing. Unfortunately, it's like the climax of this is that we're going to be able to hopefully see. Oh, wait. Oh, wait. No. Okay, well, I'm pretty sure we linked this up correctly, so that if I, went. Oh, you're really just not going to let me do that. Okay. We can sort of see it in the wires here, so it's a little disappointing to not see the light. But I can grab an extra light. That's what I'm going to do. Okay, hold on. We will not be defeated by technology. I needed an and still. Oh, shit. Okay, well. Okay, back in business. Okay, so here's my number, right? A, B, and C, D, right? So now as I've sort of doctored this, right, they're not equal, right? Because this is the numbers 0, 1, and this is the number 0, 0. So good, right? My light's off. It's saying, nope, they're not the same. And if I try to be squirrely and say, okay, how about now? So this is the number 0, 1, and this is the number 1, 0. And it says, nope, they're still not the same. But if I now, I think, try to make them the same, maybe I'll turn everybody on here, then I have the number 1, 1 and the number 1, 1, and it says, yes, those are the same. Let's see, if I try those, it says, yep, those are the same. Okay, and so on and so on. That if I make them the same, as long as I do that, I get my little light to say, yes, these are the same. All right, so, okay, good. So that's, I think I'm done with the circuit applet for the day. So that should be the correct sentence or the correct circuit that should do the check, is AB equal to CD? So, and of course I should say, right, so obviously if you have larger numbers than just 2 digits, you just make a bigger version of what we just did. If you have a three, ABC, is ABC equal to CDE, sorry, is ABC equal to DEF, you would just make sort of a larger jacked up version of what we looked at. And indeed, right, if you wanted to compare two enormous numbers together, it's just a bunch of those circuits that we just designed. All right, so the last thing I want to talk about is, so we talked about timing, we talked about comparisons, which was these last several problems of saying, how do I compare two things to each other, or compare one number to a fixed quantity and things like that. So maybe the last basic thing that I think I should be able to somehow do is basic arithmetic. So and this is it, right? So I'm not exaggerating that I know we think computers are magic in many ways and they can, play a movie for you. Honestly, when playing a movie or playing a video as you're watching this right now, all that's happening are some of these things that we just described. I know it's hard to believe that somehow a bunch of those silly circuits we just made is what's enabling you to hear me right now. But it is true, right? So an amazing, millions and billions of those little circuits coming on and off and on and off and on and off is what's making my voice come out of your computer right now and making you able to see what I'm seeing. So everything is broken down into just real simple things. So the last of the real simple things is a basic arithmetic. So, and let's just not kill ourselves here and just think about just, maybe just adding a few bits together and saying, how do I simulate, or how do I perform, so to speak, addition? Well, let's look at just a simple example of adding 2 bits, A plus B. There's obviously 4 scenarios of what I might be trying to add together, and these are the usual 4 characters, right? I might have them both zeros, 1 0 and 1 1, and or both ones, right? Now, I know this setup is making you think a little bit about hopefully a truth table. So what is it that I actually end up with? Well, when I add these numbers, I don't think I had to put the intermediate step in here, but I think we know what we get when we add these 4 combinations together. I get 0, 1, and 2 when I add these things up. Now, how do I express those? Of course, in binary. 0 I express as 0, 0. 1 I would express as 0, 1. And 2 I would express as 1, 0. Right. So over here, I've just reminded you, of course, that my answer is going to be 2 bits, and it's going to have a 2's place value and a 1's place value. Right. So how do I code, right? So just like we've been doing all day in this whole video, I want to get good at saying, all right, so how do I say, okay, for the appropriate combination of A's and B's, being zeros and ones, I want to get these, these 8 numbers over here from these 8 numbers, but correctly. Right. So, I don't know. At first glance, I'm not sure that I would even necessarily spot this, but it helps if you sort of organize your thoughts into saying, well, how do I get this bit to work, and how do I get this bit? Oh, those I think we maybe are somewhat familiar. So think about a truth table. Here's our usual 4 cases of a true, false, or zeros and ones. Just focus, I can't cover this up with my hand, but just focus on the 2's column first, right? False, 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 true, right? Or 0, 0, 0, 1. So for my usual setup of trues and falses, or zeros and ones for A and B, look at the 2's bit here. It's false, 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 true, or 0, 0, 0, 1. Huh. That sounds like a truth table or a logic operator that we're familiar with, right? In all the combinations of A and B, the only time you get a 1, or a true, is when they're both true, or both ones. Oh, that sounds an awful lot like and. And how about the other column? If I look at the ones column, I get false, true, true, false. Or in other words, I would say, how do I get this to be true? You want this to be true when 1 is true and 1 is false, but not the other 2. And that should hopefully sound like and look like the exclusive OR truth table. Oh, so, I mean, there's not a whole lot of intuition about why this exactly should work, but I think I might have discovered, or might believe, that in order to simulate addition, which is just a very basic math thing, I think I could get by with saying, all right, how do I add these two? Well, I'm going to do the AND is going to tell me what number goes in the twos column, or the twos space. And the exclusive OR of A and B should, I think, tell me what number goes in the ones column. Right? So I think this is our observation here. Oh, maybe it was easier to see in a table. Right? That for my usual combinations of zeros and ones for A and B, the response of A plus B at addition says the twos column should look like that and the ones column should look like that. And maybe we recognize, hopefully, we recognize that the ones is exclusive OR and the twos are the ands of my inputs. So the circuit that I would end up making, which I won't go back into the circuit maker, but feel free to make this one if you want, now has two outputs, right? So one important distinction is that when I'm trying to simulate addition, which is different than just asking the question, what were all the other circuits we did today? We're asking the question, should this be on or off? Should this be true or false? I just had one output, which was yes or no. But for addition, of course, well, I have to say what the answer is, right? When I add A plus B, I'm either going to get 0, 1, or 2. So I have to give you the answer. Well, I can't give you the answer in one shot. I have to tell you, since I know my answer is a 2-digit binary number, I'm going to tell you, okay, fine. I'll give you two outputs. One will be what to put in the ones column, or the ones digit, and the other will be what to put in the twos. All right, because of our observations, I think this is right. If I AND my inputs, that tells me what goes in the twos. And if I exclusive OR my inputs, which is what you see here, that should tell me what to put in the ones digit. All right, so that is exactly what your computer does. I know it sounds kind of like almost overkill, I guess, right? This seems like pretty complicated stuff just to add some ones together. But again, I know as a human, you don't think twice about saying 1 plus 1 is 2. But a computer doesn't know that. And again, it needs a circuit. It needs to be able to say, oh, okay, I need to add 1. I need to add 1 plus 1, run it through this thing, and then the output tells me what the answer is. All right, and then just very briefly, I'll mention how do you expand this? So all of these things we talked about in this video, you expand them when you have more complicated situations. So it's maybe worth just at least mentioning, how about if you wanted to add 3 bits together? So A plus B plus C. Well, here I've written out all, in this case, 8 combinations for the usual truth table, right? So I couldn't get this all in one column, but the usual truth table for 3 inputs would be, they could be false, 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 true, false, false, right? False, true, false, okay, and so on, right? So these 8 cases represent our usual 8 cases. Now I organize them sort of in numerical order, so that I could say, how do I get 0 for an answer is I do 0, 0, 0. How do I get 1 for an answer is that I have one of these is a 1 and the others are zeros. How do I get 2 for an answer? Obviously, I have 2 1s and 1 0. And the only time I ever get 3 as an answer is if they're all 1. Now, I think using the same principles that we've talked about in this whole video, you could come up with a logical sentence for this. Now, you can probably appreciate that this is going to be a little more complicated because there's 3 bits, first of all. And, well, okay, so I just have sort of a lot more to keep track of. I have a lot more cases. So rather than us sitting here and kind of contemplating, if you're really feeling ambitious and want to try to write down what the circuit would be, pause me and try it. But I'm just going to sort of show you the answer, and at least we'll agree that hopefully it makes sense. So if I think about it, right, what is it that I'm doing here is I'm saying, here's my truth table, and how do I mimic again, the same idea, the twos, what goes in the twos place and what goes in the ones place. Now I probably have to sort of do this pairwise, so it's a little bit messy, right? But we can kind of see what's happening, maybe, a little bit, which is just to say, well, when do I get a 1 in the ones place? Well, if you have 1, 1, you do, or if you have all 3 of them. So you sort of might say, if you have an odd number of ones, you'd get a 1 here. And if you have an even number of ones, like here, there's none, or here, there's 2 ones, or here is 2. That's when you get it's when you get a 0. Okay, so of course you could push comes to shove, come up with a logical sentence for that. And when do I get a 1 in the 2's column? Is when you have at least 2 ones, I think might be how you would say it, right? Okay, so could you do this? Sure. Now, right. So this would do it. So let me at least try to make a little sense of this, right? So how do I know if I have a 2's, if I have a 1 in the 2's column? Remember, what did we say? We said you need 2 of them to be true. Now this will still be okay if they're all 1s, because each one of these would be true. And since I'm connecting with ors, that's fine. Now how do I get a 1? 1 was to say, well, you want 1 or 3 1s. So A exclusive or B is going to only be on if you have one but not the other. So that'll guarantee you've got 1. And then if I do that one more time with C, then when this is off, or when this is not true, but these do give you a 1, you'll get yes. Now when this is off, maybe because A and B are both 1, then if C is also 1, this will be back on again. Okay, so it's sort of a cute way of actually doing what we described, of saying an odd number of 1s is how I know what to put in the 1s. Now this is a bit of an eyesore to look at, right? Because there's just a lot, kind of just a lot going on here. But anyway, this is the circuit that one would do if the one wanted to build one, that would say how to add 3 numbers together. Now, in reality, this does many of the things that we've talked about, I've said truthfully, do exist. This one doesn't exist in your computer. Why? It doesn't need to be able to add 3 numbers together, because it could just add 2 numbers together, take the result, and then add the 3rd number, right? So, and believe me, a computer takes all possible shortcuts to try to cut down on the amount of machinery or knowledge it needs. So this circuit, while it's cute to look at, is not necessarily a real thing that's in there. So, but it's a nice little sort of cute extension, and shows you that even for complicated things, complicated tasks like adding, it does always all boil down to just saying, all right, I can. There's always a way to come up with the right circuit to give you the right behavior. So I think this is the end. What's our takeaway? Hopefully, is that everything, right? If I haven't already convinced you by now, at this point of the course, everything really is binary. All the stuff we talked about today, which I know with circuits you get a little bit lost, but remember, everything was either just turn it off or turn it on. Everything is binary, and including not just data, which is what we spent most of the course talking about, is how do I store data. Data is sort of boring and it's very static. But to talk about action and things happening and timing of things and when do I do things and how do I know if I'm supposed to do it, this is also binary. And it's the same idea of saying, all right, I just want to sort of analyze my situations. But it's a pretty neat thing to be able to just say, okay, you come up with what circuit you need, you put it in, it turns on when you need it turns off when you don't need it. And that's really how any action that your computer ever does is via just a sequence of these circuits that some very smart and industrious person built into your computer. So, okay, so try the problems as usual. For these characters, feel free to use the applet if you want, in order to sort of test yourself. It's not a bad idea. And yeah, so that's the end of logic. So we're moving on next to actually getting to programming, which is a much, in many ways, probably much more fun topic than some of this stuff. So